46 billion light years away in every direction, there's an edge where everything we know just stops. Beyond that invisible line, the universe doesn't follow our rules anymore. Time might flow backwards, space might fold into impossible shapes, and reality itself could shatter into infinite parallel worlds. What's out there past the edge of existence? Tonight we're going to find out. Is it night where you are? Or is morning light beginning to find you? If this question pulls at something deep inside you, stay with me. A soft, like a subscribe, or just drift along. All welcome. Let's begin. Picture this. You're lying in a small boat in the middle of an ocean at midnight. Around you, lights from distant cities flicker like a glowing ring on the horizon. Beautiful, aren't they? But here's the thing. You can never swim to those cities. Not because they're too far away, but because the ocean itself is expanding. The farther from you, the faster the water flows. At some point, the water rushes faster than you could ever possibly swim. No matter how strong you are, no matter how advanced your technology, those lights will remain forever out of reach. The distance between you and them grows faster than you can close it. Now here's where it gets wild. This isn't just a metaphor. This is exactly our situation in the universe right now. The observable universe stretches about 93 billion light years across. Let that sink in for a moment. Not 93 million, not 93,000, 93 billion light years. That's the sphere of everything we can possibly see, touch, measure, or even theorize about with any certainty. Every day you see a little more of the universe, like dawn slowly revealing a landscape hidden in darkness. New light reaches us from stars that began their journey billions of years ago. But here's the heartbreaking part. Every day, galaxies are also disappearing from our reach forever, slipping past a boundary we can never cross. The universe is like a story being written in real time, but entire chapters are being erased before we can read them. In 1929, a man named Edwin Hubble changed everything. Working at Mount Wilson Observatory in California, peering through the largest telescope on Earth at the time, he discovered something absolutely terrifying. The galaxies weren't just sitting there in space, peacefully scattered like islands. They were running, fleeing, escaping from us at impossible speeds. And the farther away they were, the faster they ran. Hubble couldn't sleep for weeks after this realization. He understood what this meant. We're living in a universe that's tearing itself apart. Not violently, not catastrophically, but inexorably, relentlessly, pulling everything away from everything else. Think about that. The cosmos isn't static, isn't stable, isn't waiting for us to explore it. It's actively running away, and we're stuck here watching it go. Now here's something truly strange, something that seems to defy logic itself. The universe is only 13.8 billion years old. That's the age, the time, since the Big Bang, since the beginning of everything. But the observable universe is 93 billion light years across. Wait, what? How can a 13-year-old be 93 meters tall? How can something that's only existed for 13.8 billion years stretch across 93 billion light years of space? If you're confused, good. That means you're paying attention. The answer will surprise you more than you think, and it all comes down to something profound. Space itself has been growing. Not things moving through space, but space itself stretching, expanding, creating more distance between objects. Think of the universe as a movie. Right now, we're watching at the 13.8-minute mark. That's how long the film has been playing since the opening scene, The Big Bang. But the director has already filmed 93 minutes of footage. The universe has created that much space, that much distance, that much reality, and the rest, the parts beyond, what we can see, it might be infinite. The movie might never end. There might be no final credits, no closing scene, just an endless reel of cosmic events unfolding forever beyond our horizon. Right now, at this very moment, there's light from a distant star traveling toward Earth. It's been flying through the void for 13 billion years, longer than dinosaurs existed, longer than Earth itself has been a planet, almost as long as time itself has existed. And tonight, maybe tonight, you might be the first person in the entire universe to see it. When that ancient photon finally reaches your eye or hits a telescope's mirror, you become a witness to something that happened when the universe was young. You become connected to deep time in a way that transcends ordinary existence. Here's something that might make you smile. The universe is like your bank account. You think you know what's in there. You think you understand the balance. But the truth is, there are hidden details you haven't discovered yet. And worse, or maybe better, it's automatically expanding, without you even knowing, growing in ways you can't track or predict. Let me give you something to anchor this strangeness to your daily life. Light from the sun takes 8 minutes to reach you. 8 minutes. That means when you watch a sunset, when you feel that warmth on your face, when you see those colors painting the sky, you're not seeing the sun as it is now. You're seeing the sun as it was 8 minutes ago. The present sun. You will never see it. By the time its light reaches you, it's already the past. Now imagine that not with 8 minutes, but with billions of years. When you look at distant stars, you're seeing them not as they are, but as they were when their light began its journey. Some of those stars, they're already dead, already gone, already transformed into something else entirely. But their light is still traveling, still carrying the image of what they once were, delivering ghosts to our telescopes. You know what's the strangest thing about the universe? It's not black holes as mind-bending as they are. It's not even the Big Bang, that moment of impossible creation from nothing. The strangest thing is this. Right now, as you read these words, the space between you and the nearest star is expanding, growing, stretching, not because the star is flying away through space, but because the road between you and it is getting longer all by itself. Space isn't a stage where things happen. Space is an active participant, constantly changing, constantly growing. Let me show you how this works with something simple. Imagine your mother is baking raisin bread. You place 2 raisins close together on the dough. Now, watch what happens when the bread rises in the oven. The 2 raisins move apart, but not because they're crawling across the dough. They separate because the dough itself, the substance between them, is expanding. Now, replace the raisins with galaxies. Replace the dough with space itself. And boom, you've just understood Einstein's general relativity. You've grasped one of the most profound insights in physics. Space isn't empty, isn't nothing, isn't just a container. It's a substance that can stretch, bend, and grow. There's an invisible boundary surrounding you right now, not a wall you could touch, not a fence you could see. It's drawn with something more fundamental than matter. It's drawn with missed opportunities, with lost chances, with the fundamental limits of causality itself. This boundary is called the cosmic horizon. Everything beyond that line, you will never see it. Not in 1,000 years, not in 1,000,000,000,000 years, not if you wait until the last star burns out and the universe grows cold and dark. The light from beyond that horizon hasn't had time to reach you since the beginning of time itself, and it never will. The speed of light is 299,792,458 meters per second. That number cannot be broken, cannot be exceeded, cannot be surpassed. Not because we don't have advanced enough technology, not because we haven't discovered the right physics yet, but because that's the speed of reality itself, the rate at which cause and effect can propagate through the universe. You can't run faster than time, and light is time in motion. Light is the universe's way of connecting events, of linking cause to effect, of making the past communicate with the future. In 1905, a patent clerk named Albert Einstein couldn't sleep. He kept asking himself a seemingly silly question. If I rode on a beam of light at light speed, then held up a mirror, would I see my reflection? That absurd question overturned all of physics. It led to the realization that nothing, absolutely nothing, can catch up to light, not even other light. Time itself slows down as you approach light speed space. Itself contracts, and at light speed time stops entirely. You can't reach it, because reaching it would mean breaking the universe. Let me give you two concepts that sound similar but mean profoundly different things: particle horizon and event horizon. The particle horizon is everything that light has managed to reach you from since the Big Bang. It's your window into the past, the collection of all photons that have completed their journey to your eyes or your telescopes. This horizon is growing. Every second light from slightly farther away arrive, expanding your view. The event horizon is everything that light will still manage to reach you even in the infinite future. And here's the disturbing part. This horizon is shrinking because of dark energy, because space is expanding faster and faster. Some galaxies you can see today will eventually slip beyond this horizon. Their light will never reach you again. Think of it like this. You're in an elevator going down, but you're trying to run up the stairs. The first few floors above you, you might still reach, but the higher floors, they're moving away faster than you can climb. Eventually, they'll be forever out of reach. 70% of the universe is made of something that's actively tearing space apart. We call it dark energy, not because it's black or shadowy, but because we have absolutely no idea what it is. It's like an invisible enemy stealing galaxies from our future. Every moment, it's pushing things farther apart, making the universe lonelier, making the cosmic horizon smaller. In the distant future, civilizations that arise will look up at a night sky with far fewer stars than we see. They'll think the universe is smaller, quieter, emptier than we know it to be. We're lucky we live in an era when the universe is still close enough to see. Have you ever felt like time moves too fast? Like yesterday was just yesterday, but somehow 10 years have passed. The universe feels that way too. galaxies that were here just a cosmic moment ago are now gone forever, slipped past the point of no return. We're living in a golden moment when the universe is old enough to have structure and complexity, but young enough that we can still see most of it. Here's something that might make you smile. Dark energy is like your electricity bill. You don't see it, you don't understand how it works, but it's definitely increasing every month without fail. The event horizon is like a deadline. As the deadline approaches, your list of things you can still accomplish gets shorter and shorter. The universe has deadlines too, and some galaxies have already passed theirs forever, beyond our reach, their stories untold and unheard. But now let me tell you something even stranger, something that might keep you awake tonight, not from fear, but from pure wonder. I'm about to tell you something that physicists whisper about in dark corners, something they're almost afraid to say out loud, because it sounds insane, it sounds impossible, and yet, it might be true. Right now, at this very moment, there might be another version of you, reading this exact story, hearing these exact words, but in a completely different universe. And here's the strangest part. This is not science fiction. Imagine you have a deck of 52 playing cards. You shuffle them and deal. How many possible arrangements exist? A lot, certainly. 52 factorial. That's 52 times 51 times 50 times all the way down to 1. The number is incomprehensibly large, approximately 8 times 10 to the 67th power. But here's the key word. It's finite, limited. If you shuffled and dealt that deck enough times specifically, if you did it 52 factorial times, you would eventually mathematically, inevitably see the exact same arrangement again. The universe works the same way. There are only so many ways to arrange atoms, only so many possible configurations of matter and energy. The number is enormous, beyond human comprehension, but it's still finite. Now here's where it gets wild. If the universe is infinite in size, then every possible arrangement must occur. Not just once, but infinitely many times, including the specific arrangement of atoms that makes up you. Your memories, your thoughts, your fingerprints, the exact pattern of neurons firing in your brain, right now as you process these words. If the universe is infinite, that pattern exists somewhere else. Many somewhere else's. Mathematicians have actually calculated this. If the universe is truly infinite and reasonably uniform, there should be an exact copy of you, approximately 10 to the power of 10 to the power of 29 meters away. Let me put that number in perspective. You couldn't read all its digits if you spent your entire lifetime doing nothing but reading numbers. It's incomprehensibly, impossibly far. But in infinity, distance doesn't matter. No matter how far, if infinity exists, so does that copy of you. They're living a life almost identical to yours. Almost. Maybe they chose tea this morning instead of coffee. Maybe they turned left instead of right. Maybe they said yes when you said no. An entire parallel existence, unreachable, unknowable, but mathematically necessary if the universe truly has no end. The universe can have 3 possible shapes, 3 different geometries that determine its ultimate fate. First, positive, curvature, like the surface of a sphere. In this universe, if you traveled in a perfectly straight line long enough, you'd eventually return to your starting point, just like walking around the Earth. The universe would be finite, but have no edge, no boundary you could point to and say, here it ends. Second flat geometry, like an infinite sheet of paper. In this universe, parallel lines never meet the angles of a triangle, add up to exactly 180 degrees, and space extends forever, in all directions. This is what infinity looks like in geometric terms. Third, negative curvature, like a saddle or a Pringle chip. In this universe, space curves in a way that makes things naturally spread apart. Parallel lines diverge. Triangles have angles that sum to less than 180 degrees, and the universe expands in a particular way that's both finite and infinite at once. So, which one do we live in? Scientists have measured this with extraordinary precision using satellites like WMAP and Planck. They've looked at the cosmic microwave background, measured the angles of temperature fluctuations, calculated the curvature of space-time itself. And the answer, the universe is flat. Perfectly, precisely, impossibly flat, which means it's very likely infinite. Think about a decision you made today. Maybe something small, what to eat for breakfast, which route to take to work, whether to send that text message or let it wait. In an infinite universe, both choices happen. Both versions exist. There's a universe where you chose the foe. There's another where you chose the bun. There's one where you didn't eat at all because you overslept. There's even one where you don't exist at all because your parents never met, or because life never evolved on Earth, or because Earth itself never formed. Every possible branch of every possible decision playing out across infinite space. In 1980, a physicist named Alan Guth woke up at 3 a.m. with an idea so powerful, he immediately wrote in his notebook, "Spectacular realization," complete with exclamation point. He'd discovered cosmic inflation, the theory that in the first tiny fraction of a second after the Big Bang, specifically in about 10 to the negative 35 seconds, the universe expanded faster than light. Much faster, exponentially faster. Think of it like inflating a balloon with a compressed air tank. The balloon doesn't just grow, it explodes outward at tremendous speed. That's what happened to our universe in that first incomprehensible instant. But here's the truly mind-bending part. Inflation might never have stopped everywhere. It stopped in some places, creating pockets like ours, where galaxies can form and life can exist. But in other regions, it's still going, still inflating, still creating new space at impossible speeds. Forever, our universe might be just one bubble in an infinite foam of universes, each one a pocket where inflation happened to stop, surrounded by regions where it continues eternally. In another universe, somewhere in this infinite cosmic foam, maybe the dinosaurs never went extinct. They evolved intelligence, built civilizations, developed technology. Maybe they're looking up at their sky right now, wondering if they're alone. In another universe, maybe Hitler became a famous painter instead of a dictator. Maybe World War II never happened. Maybe history unfolded in ways we cannot imagine. In another universe, maybe you're a billionaire. Maybe you're famous. Maybe you made all the right choices and lived the life you dreamed of. In another universe, maybe you were never born at all. Maybe one small change in history meant your grandparents never met, or your parents chose different partners, and the specific combination of genes that makes you you never came together. In some universes, gravity is slightly weaker. Stars can't form. Galaxies never coalesce. Life is impossible. In some universes, electrons are heavier. Atoms can't exist. Chemistry never happens. Nothing even remotely like matter as we know it can form. But here's the heartbreaking truth. You will never meet these other yous. You will never see these other universes. The space between bubble universes expands faster than light, faster than anything can travel. They're separated not just by distance, but by causality itself, forever out of reach, forever unknowable. Have you ever asked yourself, what if? What if I'd chosen a different major in school? What if I'd taken that job offer? What if I'd been brave enough to say what I really felt? In an infinite universe, what if is not hypothetical anymore. It's happening. Somewhere. Right now. Every choice you didn't make. Every path you didn't take. Every word you didn't say. All of it is real in some distant corner of infinity. But you're here. In this universe. With the choices you made. And that makes you unique. Not because you're special in some cosmic sense, but because this specific version of you with these specific experiences exists only once in this particular bubble of reality. Good news, somewhere in the infinite multiverse, there's a version of you that succeeded brilliantly at everything you ever attempted. Bad news, there's also a universe where you've been stuck in the same Zoom meeting for 5 years straight, and no one has noticed. Best news, if you're here reading this, at least you're not the worst possible version of yourself in the multiverse. That's something, right? The infinite universe is like the Library of Babel that Jorge Luis Borges wrote about, a library containing every book that could possibly be written, every combination of letters, every possible sentence, every potential story, including the complete accurate biography of your life written before you lived it. Every thought you've had, every dream you've dreamed already transcribed and sitting on a shelf somewhere in the infinite stacks. But here's the problem. Borges identified, if the library contains every possible book, it also contains infinite books that are completely wrong, infinite books that are almost right, but differ in one crucial detail, infinite books that are nonsense from beginning to end. In infinite information, how do you find truth? That's the fundamental problem with an infinite universe. Somewhere out there, everything is real, but also everywhere out there, everything is false. You might be thinking, this story is getting crazier with every word. You're absolutely right. But that's the beauty of science. Science doesn't care whether something sounds crazy or reasonable. It only cares whether something is true or false. It follows the evidence wherever it leads, even when it leads to conclusions that seem impossible. And right now the evidence is starting to point toward a conclusion that sounds insane, but might just be correct. We live in an infinite universe, and somewhere out there, everything that can happen is happening. Now, all of this might seem abstract, distant, theoretical, but what if I told you we have a photograph, an actual image of the moment when the universe first became visible? Let me show you the oldest picture ever taken. I'm about to show you the oldest photograph ever captured. Not a black and white image from the 19th century. Not ancient cave paintings from prehistoric times, but a photograph of the universe when it was just 380,000 years old. That baby is now 13.8 billion years old, and hidden in that photograph are secrets about what lies beyond the edge of everything we know. In 1964, two engineers named Arno Penzias and Robert Wilson were going slowly insane. They worked at Bell Labs in New Jersey, operating a massive, horn-shaped radio antenna designed to detect faint signals from space. But no matter what they did, the antenna picked up noise, constant, unchanging, maddening noise. They pointed it at different parts of the sky. The noise remained. They checked the equipment. The noise persisted. They even cleaned out the antenna, removing, I'm not making this up, pigeon droppings that had accumulated inside. Surely that was causing the interference, right? The noise didn't go away. It was there when they pointed north. It was there when they pointed south. It was there in summer and winter, day and night. A persistent hiss, like static on an old radio, coming from everywhere at once. They'd accidentally discovered the echo of the Big Bang itself, the cosmic microwave background, the afterglow of creation, the light from the moment when the universe first became transparent. They were listening to 13.8 billion years of history, compressed into a whisper of microwave radiation. For 380,000 years after the Big Bang, the universe was opaque. Not dark, quite the opposite. It was brighter than anything you can imagine, hotter than the core of any star. The early universe was a plasma, soup of electrons, protons, and photons all mixed together at temperatures of billions of degrees. Photons couldn't travel more than a tiny distance before colliding with an electron. Light couldn't stream freely through space. It was trapped, scattered, bounced around like a ray of sunlight, trying to penetrate thick fog. If you'd been there, which is impossible for many reasons, you couldn't have seen anything. Not because it was dark, but because light couldn't travel. Your flashlight would illuminate nothing. The beam would scatter and reflect back instantly. It would be like being inside the sun itself, surrounded by blazing plasma so thick that vision itself becomes meaningless. That's why the cosmic microwave background is called the wall of time. It's not a wall in space. It's a wall in the past, a barrier beyond which we cannot see, because light itself was trapped. After the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, a moment called recombination, the photons were finally free. They streamed outward in all directions, carrying with them a snapshot of what the universe looked like at that moment. Those photons have been traveling ever since. Stretched by the expansion of space, red-shifted from visible light into microwaves, but still carrying their ancient message. That's what Penzias and Wilson heard the whisper of creation itself. After the CMB photons escaped, something strange happened. The universe plunged into absolute darkness. Scientists call this the cosmic dark ages, and the name is perfectly accurate. There were no stars yet, no galaxies, no light sources of any kind, just cold hydrogen gas slowly collapsing under its own gravity, gathering into clumps that would eventually ignite, but not yet. Not for hundreds of millions of years. If you could somehow exist in this era, if the laws of physics allowed it, you wouldn't see your hand in front of your face. Not because your eyes were inadequate, but because there was literally no light anywhere in the universe. No photons traveling between stars. because there were no stars, just darkness, cold and complete, and absolute stretching across billions of light years. This dark age lasted roughly 100 to 200 million years. In cosmic terms, that's quick. In human terms, it's longer than life has existed on Earth. The universe sat in darkness, brewing the ingredients for its next act, gathering the raw materials for the first stars. In 2001, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP. Its mission was singular and ambitious photograph the cosmic microwave background with unprecedented detail, map the ancient light, measure the temperature variations across the sky to a precision of millionths of a degree. It succeeded. WMAP produced the most detailed map of the infant universe ever created, revealing patterns and structures that told us how galaxies would eventually form, how the universe would evolve, even what the universe is made of. Then, in 2013, the European Space Agency did something even more impressive. They launched the Planck satellite, which measured the CMB with even greater precision. They detected temperature differences of just 1 part in a million, like measuring the difference in height between two mountains that are both exactly 1,000 meters tall, but one is taller by the width of a human hair. And in those tiny temperature variations, cosmologists could see the seeds of galaxies, slightly warmer spots where matter was slightly more dense, where gravity was beginning to pull things together. Billions of years later, those spots became clusters of galaxies. The baby picture of the universe was also a prophecy of its future. Then something miraculous happened. The first stars ignited. Not stars like our sun, these were monsters. Population 3 stars, as astronomers call them. Stars 100 times more massive than the sun, burning at incomprehensible temperatures, blazing with the light of millions of our stars. Their radiation flooded outward, hitting the neutral hydrogen that filled the universe. The energetic photons ripped electrons away from atoms, ionizing the gas, making the universe transparent again. It's called reionization, the universe being reborn into light. Imagine being in a room that's been completely dark for 100 million years. Then someone flips a switch. The lights don't just turn on, they explode into brilliance. That's what happened. Scientists call it the cosmic dawn. The James Webb Space Telescope right now is trying to see that moment. It's looking back through time, searching for the light from those first stars, trying to witness the instant when the universe woke up. But here's what they don't advertise widely. Here's what whispered about in conference rooms and late-night discussions among cosmologists. In the maps of the cosmic microwave background, there are anomalies, spots that shouldn't exist, regions that are slightly colder or slightly warmer than our best theories predict. The famous cold spot, a vast region of the sky that's measurably colder than it should be. Some scientists, the brave or perhaps foolish ones, whisper a possibility these anomalies might be scars, evidence of our universe colliding with another universe before we were born, bruises from a cosmic impact that happened before time itself began, at least before time as we understand it. Most of their colleagues say, don't be ridiculous. Don't see patterns where there's only noise. The cold spot is probably just statistical fluctuation, they argue. A cosmic coincidence. Nothing more. But the whispers continue, and we'll come back to this mystery later because it might be one of the most important clues about what lies beyond the edge. Do you have an old television? The kind that shows static snow when there's no signal? Most people don't anymore. But if you do look at it carefully, about 1% of that static, those random dancing dots, is the cosmic microwave background. You're literally seeing the Big Bang with your own eyes on your TV screen. Every time your television shows static, you're looking at light that's been traveling for 13.8 billion years. It's not distant. It's not abstract. It's here, right now, passing through your body, hitting your antenna, displaying itself as noise on your screen. The CMB is like the universe's baby picture. And like all baby pictures, it's a bit blurry, a bit reddish from the long journey. And the parents, in this case cosmologists, can't stop showing it to everyone and explaining what every little detail means. The cosmic dark ages are like that period between turning off the lights and falling asleep. Everything goes dark. You hear only your own breathing. The world seems to disappear. Then dawn arrives. Light floods back in, and a new day begins. The universe had its own dawn. After hundreds of millions of years of darkness, the first stars lit up, and the cosmos began the brilliant, complex, beautiful phase that continues today. The age when galaxies form, when planets orbit stars, when life becomes possible. And we're lucky enough to live in that age, to witness that light, to ask these questions under a sky full of stars. Now let me tell you the saddest story in all of cosmology. Not about shooting stars burning up in our atmosphere, not about supernovae exploding in brilliant death, but about goodbyes that are never spoken, about galaxies silently vanishing from our universe one by one, slipping past a horizon we can never cross, and we can do nothing. We can only watch. In 1995, astronomers made a decision that seemed almost foolish. They pointed the Hubble Space Telescope at a tiny patch of sky near the Big Dipper, a spot that appeared completely empty. No visible stars, no obvious galaxies, just darkness. They called it the Hubble Deep Field. The region they chose was impossibly small. Hold a grain of sand at arm's length. That's how much sky they were looking at. A speck, a nothing. Colleagues questioned the wisdom of dedicating 10 consecutive days of precious telescope time to photograph emptiness. But they did it anyway. For 10 days, Hubble stared at that dark patch, collecting every photon it could, gathering ancient light that had traveled incomprehensible distances. When the image came back, astronomers gasped. In that tiny speck of empty sky, they found more than 3,000 galaxies. 3,000 entire galaxies in a space smaller than a grain of sand held at arm's length. Multiply that across the entire sky, across every direction you could point a telescope. The mathematics are staggering. 2 trillion galaxies, not 2 million, not 2 billion, 2 trillion distinct galaxies, each containing hundreds of billions of stars scattered across the observable universe. This number exceeds human comprehension. Your brain cannot truly grasp it. If you counted one galaxy per second, never stopping to eat or sleep, it would take you more than 60,000 years to count them all. And that's just the ones we can see. But here's the bad news. The heartbreaking truth that keeps cosmologists awake at night. Dark energy is pushing these galaxies apart, faster and faster, accelerating. Some galaxies you can see tonight shining faintly in telescopes are already doomed. In 1 billion years, they'll grow dimmer. Their light will redshift, stretching toward longer wavelengths as space expands between us. In 10 billion years, gone completely, not because they died or burned out, but because the space between us and them has grown so vast that their light can no longer complete the journey. The photons will stretch and redshift until they carry no energy at all, invisible, unreachable, lost. The light from those galaxies will never arrive again, ever. Imagine the distant future trillions of years from now. If intelligent life somehow still exists on Earth, or on whatever world orbits whatever star remains, in this corner of space they'll look up at their night sky and see almost nothing, just 30 to 40 galaxies, the nearest ones. The local group, our galactic neighborhood, bound together by gravity fighting against the expansion. Andromeda, the Magellanic Clouds, a handful of dwarf galaxies. That's it. Everything else. The entire rest of the sky, pure black, absolute darkness, empty. They'll think the universe contains only them and their nearest neighbors. They'll believe they're alone in a small, quiet cosmos. And they'll be right. In their observable universe, they will be essentially alone. The truth that trillions of galaxies once filled the sky, that the universe was once rich and crowded and full of light, that truth will be gone. No evidence will remain. Future astronomers won't even know what they're missing. Every second, 20,000 stars slip beyond our cosmic horizon. 20,000 stars cross the boundary from observable to forever unreachable. Not because they explode or fade, not because they move through space, but because space itself expands so fast that their light cannot overcome the distance anymore. Think about an old friend who moved to another country. At first you stay in touch, phone calls, messages, but over time the connection weakens. Phone numbers change. Social media accounts go dormant. Eventually, you can't reach them anymore. You forget their face. The details blur. But they're still out there, still alive, still living their life. They're just no longer part of your world. The galaxies are like that. They're not dying. They're not vanishing from existence. They're simply leaving our world, crossing into a realm where we can never follow, where their light can never reach us, where they become, for all practical purposes, gone. But there's good news hidden in this tragedy. There's a silver lining to this cosmic goodbye. We're living in something special, something precious. Cosmologists call it the golden age of observation. The universe right now is old enough to have developed complex structure. Galaxies have formed. Stars have ignited. Heavy elements have been forged in supernovae and scattered across space. Planets orbit. Life exists. Intelligence has emerged to ask questions and build telescopes. But the universe is also young enough that we can still see most of it. The distant galaxies haven't slipped away yet. The light from the early universe still reaches us. We live in this perfect window, old enough to understand, young enough to observe. 100 billion years from now, future scientists will envy us. They'll look at whatever records remain from our era, if any survive that long, and they'll feel a profound jealousy, because they'll never see what we're seeing right now, never witness the cosmic web of galaxies, never observe the distant light from the universe's youth. Their sky will be dark and empty, and they'll never know what they lost. We're the lucky ones. We exist in this brief cosmic moment when the universe reveals itself. In July 2022, the James Webb Space Telescope sent back its first images. Among them was a galaxy, a faint smudge of light that existed 13.5 billion years ago. 13.5 billion light years away. Let that sink in. We're seeing this galaxy as it was when the universe was only 300 million years old. A baby universe. Stars just beginning to form. Galaxies just starting to coalesce from clouds of primordial hydrogen. But here's the question that haunts astronomers. Where is that galaxy now? Right now, in this moment, what does it look like? Nobody knows. Nobody can know. Maybe it's dead. Its stars burned out. Its gas exhausted. Collapsed into a graveyard of white dwarfs and black holes. Maybe it's thrived, grown into a massive spiral galaxy with billions of stars, planets, perhaps even civilizations, asking the same questions we're asking. We'll never know. The light showing us its now won't arrive for another 13 billion years. And by then we'll be gone. Humanity will be gone. Earth itself will be gone. Even the sun will have burned out. We're looking at ghosts. Ancient ghosts. Images of things that existed so long ago that they might as well be dreams. Have you ever looked at an old photograph and realized the person in it has completely changed? Maybe they're no longer alive. Maybe they've become someone entirely different, aged, transformed, unrecognizable. Every time you look at stars, you're looking at old photographs of the universe. Those stars you see tonight, they might already be dust. The light you're seeing left them thousands, millions, even billions of years ago. By the time it reaches your eyes, the source may have already transformed into something else entirely, or vanished completely. That light is all that remains of a past that's already gone. It's a message in a bottle thrown across cosmic time, finally arriving to tell you about something that no longer exists in the form you're seeing. When you look up at the night sky, you're not seeing the universe as it is. You're seeing a museum of the past, a collection of old images, each one showing you a different moment in history, all arriving simultaneously at your retina. The moon as it was 1 second ago. The sun as it was 8 minutes ago. Alpha Centauri as it was 4 years ago. Distant galaxies as they were billions of years ago. The universe's present is something you will never see. By the time light brings you information, it's already history. But here's something that might make you smile something to lighten this cosmic melancholy. At least the galaxies aren't ghosting us on purpose. They're not ignoring our messages, not leaving us on read and refusing to respond. They can't reply because physics won't allow it, not because they're being rude. The distant galaxies would love to send us their light, but space won't let them. The expansion is too fast. The distance is too great. It's not personal. It's just the universe doing what the universe does. Think of distant galaxies like elderly relatives in a nursing home. You can visit them now. You can sit with them, hear their stories, see their faces. But you know deep in your heart, you know that one day they'll be gone. And after that, only memories remain. Only the photographs. Only the stories you tell about them to others who never met them. The universe is the same way. We can observe these distant galaxies now. We can study them, photograph them, measure their properties. But we know their light is fading. We know that someday, not in our lifetime, not in humanity's lifetime, but someday they'll slip past that horizon. and be gone forever. So cherish what we can still see. Appreciate this golden age. Look up at the night sky and know that you're witnessing something temporary, something precious, something that won't last forever. The galaxies are waving goodbye, slowly, silently, inevitably, and we're standing here watching them go, unable to follow, unable to stop them, only able to remember them as they fade into the expanding darkness. This is the universe we live in, beautiful, vast, tragic, and fleeting, and we're lucky enough to see it while it's still visible. But now let me take you somewhere even stranger, because beyond these disappearing galaxies, beyond the edge of what we can see, there might be something else entirely. Not just more space, not just more galaxies, but other universes, infinite bubbles of reality, each with their own laws, their own physics, their own strange and impossible characteristics. Are you ready? Let's step beyond the edge. What if I told you that our universe, this vast expanse containing 2 trillion galaxies stretching 93 billion light years across, is just one bubble in an infinite ocean of bubbles? What if everything you've ever known, every star you've ever seen, every law of physics you've ever learned applies only to our tiny pocket of reality? What if there are other bubbles, other universes, floating right next to ours, separated by nothing more than a thin membrane of space itself? And what if we can never ever reach them? Welcome to the theory of eternal inflation and the bubble multiverse, one of the most mind-bending ideas in modern cosmology. Remember cosmic inflation, that moment in the first fraction of a second after the Big Bang, when the universe exploded outward faster than light, growing from smaller than an atom to larger than a galaxy in less time than it takes light to cross a proton. That inflation solved many problems in cosmology. It explained why the universe is so uniform, why space appears flat, why we don't see certain exotic particles that should have been created in the Big Bang. Inflation was revolutionary. It changed everything. But here's where it gets truly strange. Inflation might never have stopped. Not everywhere, at least. Think of inflation like boiling water. When water boils, bubbles form pockets where the water has transformed into steam, surrounded by liquid that's still boiling. Each bubble represents a phase transition, a region where the state has changed. The universe might work the same way. Inflation is like the boiling. It's still happening in most of space, expanding faster and faster, creating more and more volume. But occasionally, randomly, quantum fluctuations cause inflation to stop in certain regions. Those regions become bubbles, universes, like ours. Our observable universe, everything we can see is inside one such bubble. Inflation stopped here 13.8 billion years ago, and space began expanding at a normal rate. Galaxies formed, stars ignited, planets coalesced, life emerged. But beyond our bubble, inflation is still raging. Space is still exploding outward at impossible speeds, creating infinite volume, infinite possibilities. And within that eternally inflating space, other bubbles are constantly forming. Other universes, each one with its own Big Bang, its own history, its own potential for galaxies and stars and life. This is called eternal inflation, and it's not just speculation. It emerges naturally from our best theories of quantum field theory and cosmology. If inflation happened once, It's almost impossible for it to stop everywhere simultaneously. It should continue forever in most places, creating an endless multiverse of bubble universes. Picture an ocean of soap bubbles, millions upon millions of them, each bubble separate from the others, each one containing its own little world. Some bubbles are large, some are small, some last for a long time, others pop almost immediately. That's the multiverse. Our universe is one bubble in an infinite foam of universes, each one isolated from the others by regions of space that are still inflating, still expanding faster than light can travel. And here's the truly wild part. Each bubble universe might have different laws of physics, different fundamental constants, different particles, different forces. The rules that govern reality might be unique to each bubble. Why? Because the laws of physics, as we know them, aren't necessarily fundamental. They emerge from something called symmetry, breaking when the universe cooled. After the Big Bang, certain symmetries were randomly broken, determining which particles exist, how strong gravity is, what the speed of light is, whether atoms can form. In our bubble, the symmetries broke one way. Gravity has a certain strength. The electron has a certain mass. The electromagnetic force works a certain way. But in another bubble, the symmetries might break differently. Gravity might be stronger or weaker. Electrons might not exist. The fundamental constants might have completely different values. Some bubbles might have stronger gravity, so strong that stars collapse immediately into black holes, never burning long enough to forge heavy elements. No planets, no chemistry, no life. Some bubbles might have weaker nuclear forces, so weak that atomic nuclei never were. Just a universe filled with individual protons and electrons, never combining, never creating the complexity necessary for anything interesting. Some bubbles might have more dimensions of space, or fewer. Some might have time running differently, multiple time dimensions, or time that loops back on itself. Some might not have electromagnetism, or might have completely different forces we can't even imagine. The multiverse isn't just infinite in size, it's infinite in variety. Every possible configuration of physical laws, every possible value for the fundamental constants exists somewhere in some bubble. And here's something even stranger. Some bubbles might not even last. They might be unstable, forming briefly during a quantum fluctuation, then collapsing or exploding before they can develop any structure. Like soap bubbles that pop the instant they form. Stillborn universes that never had a chance to become anything. Our universe is lucky. We formed in a bubble where the constants are just right. Not too much gravity, not too little. The nuclear force is strong enough to forge atoms, but weak enough to allow stars to burn for billions of years. The expansion rate just right to allow galaxies to form. We're Goldilocks universes, not too hot, not too cold, but just right. Think of the multiverse like a massive apartment complex. Infinite floors, infinite apartments, each one decorated differently by different tenants with different tastes. Some apartments are lavish and complex, filled with art and life and activity. Others are bare and simple empty rooms with nothing in them. Some are bizarre, arranged in ways that don't make sense to outsiders. You live in one apartment. You've decorated it with galaxies and stars and planets. It feels like home. But right next door, separated by a thin wall you can never break through, there's another apartment with completely different furniture, completely different rules about what's allowed, and you'll never visit, never peek inside, never know what it looks like. Do you ever feel lonely, like you're isolated, cut off alone in existence? But what if I told you that right now, right this instant, just beyond a thin layer of space, you cannot perceive there might be another entire universe, another reality with its own galaxies, its own stars, its own beings looking up at their sky and wondering if they're alone? They're as close as the next room, but you'll never open the door. Physics won't allow it. The space between bubbles expands faster than anything can travel. You're separated not by distance, but by causality itself. It's the ultimate loneliness surrounded by infinite neighbors you can never meet. But here's something that might make you smile. If there are other universes, other bubbles, with their own laws and constants and possibilities, let's hope they have better Wi-Fi than we do. Let's hope their version of physics doesn't have frustrating things like dropped connections and buffering videos. Although, to be fair, if their electromagnetic force is different, they might not have Wi-Fi at all. They might not even have light, just darkness, gravity, and strange forces we don't have names for. The bubble multiverse raises profound questions. Are these other universes real if we can never observe them? If something exists but can never affect us, never send us information, never interact with our reality in any way? Does it exist in any meaningful sense? Scientists are divided. Some say the multiverse is a legitimate prediction of our best theories, and we should accept it even if we can't observe it directly. Others say it's unfalsifiable, impossible to test, and therefore not science at all, just mathematical speculation. But here's what we know. The equations point toward eternal inflation. The math suggests bubble universes. Our theories, when followed to their logical conclusion, predict a multiverse, whether we like it or not. And sometimes the universe doesn't care what we find comfortable or intuitive. Sometimes reality is stranger than we want it to be. But if bubble universes feel hard to grasp, let me show you something even more bizarre. A theory where our entire three-dimensional universe is just a thin membrane floating in a higher dimensional space we cannot perceive. Imagine you're a fish. You've lived your entire life in a pond. You swim left, right, forward, backward. You understand two dimensions perfectly. The surface of the water is your world. But there's a dimension you don't perceive up and down. Above your pond is air, sky, clouds, birds. Below is mud, rocks, earth. An entire reality exists in directions you cannot move, dimensions you cannot access. What if we're like that fish? What if our three-dimensional universe, all of space as we know it, is just a surface, a membrane floating in a higher dimensional space we cannot perceive? This is brain cosmology, and it comes from string theory, one of the most ambitious attempts to unify all of physics into a single framework. String theory proposes that the fundamental building blocks of reality aren't particles, but tiny vibrating strings of energy. Different vibration patterns create different particles, electrons, quarks, photons, all just different notes played by the same cosmic instrument. But here's the catch: string theory only works mathematically if there are more than 3 dimensions of space. Depending on the version, string theory requires 10 or even 11 total dimensions, 9 or 10 spatial dimensions plus time. Where are these extra dimensions? Why don't we see them? The most common explanation is that they're compactified, curled up so small that we can't detect them, rolled into shapes smaller than atoms, smaller than protons, smaller than anything we can measure. But brain cosmology suggests something different. Maybe some of those extra dimensions aren't compactified. Maybe they're extended large real. And maybe our entire universe, everything we've ever observed, is confined to a 3-dimensional membrane, a brain floating in this higher dimensional space called the bulk. Think of it like sheets of paper stacked in a notebook. Each sheet is a 2-dimensional surface. You can move left and right, up and down on the paper. But to move between pages, you need to travel in a 3rd dimension through the space between the sheets. Now add one more dimension to that analogy. Our universe is a 3-dimensional brain, like a sheet of paper, but with one more dimension. We can move left, right, forward, backward, up, down, but there are additional dimensions, perpendicular to all of those dimensions, we cannot access, cannot perceive, cannot move through. The bulk, the higher dimensional space, surrounds our brain. It might be millimeters away, in a direction we cannot point to, or it might be infinite. We don't know, because we're stuck on our brain, unable to step off into the bulk. But here's where it gets interesting. Most forces and particles are confined to the brain. Electromagnetism, the strong nuclear force, the weak nuclear force, they all exist only on our membrane. They cannot leak into the bulk. But gravity might be different. Gravity might be able to seep into the extra dimensions, spreading out into the bulk in ways that other forces cannot. This could explain one of physics' greatest mysteries. Why is gravity so weak compared to the other fundamental forces? Electromagnetism is vastly stronger than gravity. The nuclear forces are incomprehensibly more powerful. If you hold a magnet to a refrigerator, that tiny magnet's electromagnetic force overcomes the gravitational pull of the entire Earth. Why? Maybe because gravity isn't fully confined to our brain. Maybe it leaks. Most of gravity's strength spreads out into the bulk, into dimensions we cannot access, and only a tiny fraction remains on our 3-dimensional membrane. The gravity we experience is just the residue, the leftover, the small portion that didn't escape. If this is true, then there might be other brains out there in the bulk, other 3-dimensional universes floating parallel to ours, separated by a tiny distance in a direction we cannot perceive. You're sitting in a room right now, or lying in bed, or walking down a street. What if just 1 millimeter away from you in a higher dimension, there's another entire universe, another 3-dimensional space, with its own galaxies, its own stars, its own planets, maybe even its own version of Earth, its own version of you. You'll never see it, never touch it, never know it's there, because you cannot move in that direction. Your body, your atoms, your electromagnetic interactions are all confined to this brain. You're stuck on this surface, just like a drawing on paper is stuck on its page. But gravity connects you. Gravity from that other brain might seep into our universe, and our gravity might seep into theirs. You might literally feel the gravitational influence of another universe without ever knowing it. It's like looking at the surface of a pond. You see water insects skating across the surface, moving in 2 dimensions. They don't know that beneath them, fish are swimming, living entire lives in a dimension the insects cannot perceive. The insects might feel subtle ripples, gentle disturbances in the water, never knowing they're caused by fish moving below. We might be those insects, and the fish, other universes in the bulk. There's an even more radical version of brain cosmology called the ekpyrotic universe. In this model, the Big Bang wasn't the beginning of everything. It was a collision, 2 brains floating in the higher dimensional bulk, slowly moving toward each other. When they collided, the impact released enormous energy, enough to create everything we see, everything we know. The Big Bang from this perspective wasn't an explosion from a singularity. It was a crash between universes, like 2 cosmic cymbals slamming together, creating a sound, our reality from their collision. After the collision, the brains bounced apart. They're moving away from each other now, but gravity might eventually pull them back. In trillions of years, they might collide again. Another Big Bang, another universe, an endless cycle of creation and destruction, brains bouncing back and forth through the bulk for eternity. Our universe isn't unique. It's just one percussion in an infinite cosmic drum solo. The hidden dimensions are like radio frequencies. Right now, all around you, radio waves are passing through your body. M radio, FM radio, Wi-Fi signals, cell phone transmissions. They exist. They're real. They carry information, but you can't hear them without a radio receiver tuned to the right frequency. Your ears don't detect those frequencies. They're outside your perceptual range. But that doesn't mean they're not there, not real, not carrying messages and music and data right through your living room. Extra dimensions might be like that, real, present all around us, but tuned to a frequency we cannot perceive. Our senses, our instruments, our entire existence is tuned to 3 spatial dimensions. We're blind to the others, deaf to their signals, unable to access them, without tools we haven't invented and maybe cannot invent. Brain cosmology is still speculative. We don't have direct evidence yet, but experiments are searching. The Large Hadron Collider looks for signs of extra dimensions, particles that appear to vanish energy, that seems to disappear subtle anomalies that might indicate something escaping into the bulk. So far, nothing conclusive, but the search continues. And if we ever detect proof of extra dimensions, proof of other brains, it will revolutionize everything. Our understanding of physics, of cosmology, of reality itself will transform overnight. You're not alone in your universe. You might be surrounded, literally surrounded by other universes, other realities, other worlds. They're just hidden in dimensions your eyes cannot see, in directions your body cannot turn. The bulk is out there, maybe close, maybe far. We just haven't learned to look in the right direction yet. Now, if extra dimensions and parallel brains sound strange, prepare yourself for something even more unsettling. A theory that suggests everything you've ever experienced might be a projection from somewhere else. What if I told you that you're not real? Not in the way you think you are. At least, what if your 3-dimensional body, your thoughts, your memories, your entire existence is actually encoded on a distant 2-dimensional surface? What if you're a hologram? This isn't science fiction. This is the holographic principle, one of the most profound and bizarre ideas in theoretical physics. and it emerged from studying the strangest objects in the universe, black holes. In the 1970s, a physicist named Jacob Bekenstein made a curious discovery while studying black holes. He was trying to understand their entropy, a measure of disorder of how much information a system contains. For most objects, entropy scales with volume. A larger box of gas has more entropy than a smaller box because it has more space for particles to arrange themselves in different configurations. Volume determines information capacity, but black holes don't follow this rule. Bekenstein found something shocking. A black hole's entropy doesn't depend on its volume, it depends on its surface area, specifically on the area of its event horizon, the boundary beyond which nothing can escape. Stephen Hawking later confirmed this with more rigorous calculations. The amount of information a black hole can contain is proportional to the area of its event horizon, not the volume inside. One bit of information per Planck area, the smallest possible unit of space, about 10 to the negative 35 meters squared. Think about how strange this is. Imagine a sphere. Common sense says the amount of stuff you can fit inside depends on the sphere's volume, how much space is inside. But black holes say no. It depends on the surface how much area the boundary has. It's like saying a room's storage capacity depends on its wallpaper, not on the space inside. Bizarre, counterintuitive, and yet mathematically true. This led to a radical proposal. Maybe black holes aren't special. Maybe this is how the entire universe works. Maybe all the information in any volume of space, any region, any size, is actually encoded on the boundary surface of that region. Gerard 't Hooft and Leonard Susskind formalized this in the 1990s, proposing the holographic principle. The idea is simple, but mind-bending. All the information about what happens inside a volume of space can be encoded on the surface that surrounds it, like a hologram, where a three-dimensional image is stored on a two-dimensional surface. You've seen holograms, those images, on credit cards or special stickers that appear three-dimensional. When you tilt them, the entire three-dimensional picture is encoded in a flat, two-dimensional surface through interference patterns. Shine light on it properly, and depth appears. The third dimension emerges from information stored in two dimensions. The holographic principle suggests the universe works the same way. Everything, every particle, every force, every event in three-dimensional space might be encoded on a distant two-dimensional boundary, and we living our three-dimensional lives are the projection, the hologram. In 1997, a physicist named Juan Maldacena made a breakthrough that gave the holographic principle mathematical teeth. He discovered something called the ADAS-CFT correspondence, a relationship between two very different theories of physics. On one side, a theory of gravity in a curved space called anti-de Sitter space, with a certain number of dimensions. On the other side, a quantum field theory without gravity, living on the boundary of that space, with one fewer dimension. Maldacena proved these two theories are equivalent, completely equivalent. Anything you can calculate in the gravitational theory, you can also calculate in the boundary theory. They're two descriptions of the same reality, one with gravity and more dimensions, one without gravity and fewer dimensions. It's like having two languages that translate perfectly into each other. A three-dimensional world with gravity is mathematically identical to a two-dimensional world without gravity. The boundary theory is simpler, easier to calculate, but describes the exact same physics. This suggests something profound. Maybe our universe is also a hologram. Maybe the four-dimensional space-time we experience, 3 dimensions of space plus time, is actually encoded on a 3-dimensional boundary somewhere, and we're living in the projection, the cosmic horizon, the edge of the observable universe, 46 billion light years away in every direction might be that boundary. Everything that happens inside our observable universe, every particle interaction, every thought you've ever had, might be encoded as information on that distant surface. You're not living in 3 dimensions. You're a projection from a 2-dimensional screen, experiencing the illusion of depth. Have you ever felt like life is a movie? Like you're watching events unfold on a screen? Like there's something slightly unreal about existence? Maybe you're right. Maybe in a very literal scientific sense, you are part of a projection. Not a movie exactly, but a hologram 3-dimensional experience generated from 2-dimensional information. This connects to another wild idea, the simulation hypothesis. What if the universe is a computer simulation? What if some advanced civilization created our reality as a program running on their computers? The holographic principle doesn't prove we're in a simulation, but it does suggest reality might be more like information like data than we thought. If the universe can be described by information on a boundary, then maybe that boundary is like a computer memory. Maybe the universe is in some sense computational. But here's something that might make you smile. If we are holograms, at least we're high-resolution holograms. The amount of information encoded on the cosmic horizon is staggeringly vast, more bits than you could count if you spent every moment from now until the heat death of the universe doing nothing but counting. We're not pixelated, not blurry. We're rendered in exquisite detail. The holographic principle is still being tested, still being explored. Some physicists think it's profound a deep truth about how information works in the universe. Others think it's just a mathematical curiosity that doesn't tell us anything fundamental about reality. But here's what we know the math works. The equations point toward holography. Our best theories of quantum gravity, our attempts to reconcile quantum mechanics with general relativity, keep leading us back to this idea that reality might be a projection, that dimensions might emerge from information encoded on surfaces, that the universe might be less solid than we think. At this point, the story is getting stranger, isn't it? But that's the beauty of the universe. It doesn't care about our intuitions. It doesn't respect what seems reasonable. It simply is what it is, and what it is turns out to be far stranger than we ever imagined. We started with galaxies disappearing beyond the horizon. Now we're discussing whether reality itself is a hologram. The journey into understanding what lies beyond the edge has taken us to places we never expected, and we're not done yet. But if holographic projections feel too abstract, let me tell you about something that might be even more mind-bending, a mirror universe running backward through time. What if there's another universe on the other side of the Big Bang, not in space, not in another dimension, but in time? A universe where everything runs backward, where cause and effect reverse, where entropy decreases instead of increases. A perfect mirror of our reality reflected across the moment of creation. This is the anti-universe hypothesis, and it's based on one of the most fundamental symmetries in physics, CPT symmetry. CPT stands for three transformations. C for charge swap all particles, with their antiparticles turning matter into antimatter. P for parity flip spatial coordinates, like looking in a mirror, turning left into right. T for time reverse the direction time flows, making the future become the past. Physics has a deep principle. If you apply all three of these transformations simultaneously, flip charge, flip space, flip time, the laws of physics should remain unchanged. CPT symmetry is fundamental. Every force, every interaction, every process in nature respects it. But here's something strange. Our universe doesn't look CPT symmetric. Time flows in one direction. The universe contains far more matter than antimatter. Things seem asymmetric, lopsided, unbalanced. Some physicists wondered, what if the symmetry isn't broken? What if it's just hidden? What if the Big Bang created not one universe, but two ours, moving forward in time and another moving backward? A mirror universe on the other side of the moment of creation. In this model, the Big Bang isn't the beginning of time. It's a boundary, a dividing line. On one side, our universe expands forward into the future. On the other side, the anti-universe expands backward into the past. From our perspective, it's running in reverse. From their perspective, they're normal, and we're the weird ones running backward. Imagine playing a video in reverse. Everything looks strange. Water flows upward, broken glass reassembles itself, people walk backward. But if you were inside the video, if you were one of those people, would you notice? No. Your memories would also be reversed. Your perception of cause and effect would flip. To you, everything would feel normal, would feel like it's moving forward. The anti-universe would be like that. To beings in that universe, time flows forward just as it does for us. They remember the past and anticipate the future. They experience entropy, increasing disorder, growing. But from our external perspective, they're moving backward through time. It's like two mirrors facing each other. You stand between them. In one mirror, you see yourself normally. In the other mirror, you see a reflection. Both versions think they're the real one. Both versions see the other as reversed. This anti-universe would be made of antimatter from our perspective. But remember, antimatter is just matter with opposite charge. To inhabitants of the anti-universe, their particles are normal matter and ours are antimatter. It's all relative, all a matter of perspective. This theory solves a major puzzle. Why does our universe have more matter than antimatter? The Big Bang should have created equal amounts of both. When matter and antimatter meet, they annihilate, turning into pure energy. If the Big Bang produced them equally, they should have destroyed each other, leaving nothing but light. But our universe clearly has leftover matter, lots of it. Galaxies, stars, planets, you all made of matter, with barely any antimatter around. Where did the antimatter go? The anti-universe hypothesis says nowhere. It didn't go anywhere. It's on the other side of the Big Bang in the anti-universe. The symmetry isn't broken. It's just separated. There's another intriguing piece of evidence. Neutrinos, ghostly particles that barely interact with anything, come in three types, and all of them are left-handed. This means their spin points opposite to their direction of motion. It's a strange asymmetry. Most particles come in both left and right-handed versions, but neutrinos seem to be only left-handed. But what if right-handed neutrinos do exist? What if they're in the anti-universe? That would restore the symmetry. Left-handed neutrinos in our universe, right-handed neutrinos in the anti-universe. Perfect balance. Some physicists even suggest these right-handed neutrinos from the anti-universe might be what we call dark matter, the invisible substance that makes up most of the matter in the universe. We can't see dark matter with telescopes because it doesn't interact with light. What if it's from the anti-universe, leaking through somehow affecting our gravity, but nothing else? It's speculative, but intriguing. The anti-universe might not be completely separated from ours. There might be subtle connections, faint interactions, whispers from the other side. The anti-universe isn't somewhere else in space. It's not in another dimension. It's on the other side of time itself. If you could somehow travel backward through the Big Bang, which physics says is impossible, but imagine anyway, you wouldn't find nothingness or a singularity. You'd find another universe, expanding in the opposite temporal direction. Think about it like this. You're watching a movie. You press rewind. The characters walk backward, speak in reverse. Events unfold in opposite order. But from inside the movie, from the character's perspective, nothing has changed. They're still experiencing their story moving forward. It's only you, the external observer, who sees it running backward. The anti-universe is us on rewind, or maybe we're them on rewind. It's impossible to say who's forward and who's backward. Both perspectives are equally valid. This theory is beautiful, elegant, symmetric, but it's also untested. We have no direct evidence of an anti-universe. We can't observe it, can't measure. It can't confirm it exists. It remains a theoretical possibility, a mathematical solution to symmetry problems, a way to make the equations balance. But sometimes the universe surprises us. Sometimes the elegant mathematical solution turns out to be true. Sometimes symmetry wins. And if it does, if the anti-universe exists, then we're not alone in time. We have a twin, a mirror, a reflection on the other side of creation. We'll never meet them, never communicate with them, never know them. But they're there, moving through time in the opposite direction, experiencing their own version of reality. Two universes, born together, moving apart through time, forever separated but eternally connected by the moment they both emerged from the Big Bang, that singular instant when everything began, or rather, when everything split into forward and backward, into us, and them into universe and anti-universe. But what if the Big Bang wasn't the beginning at all? What if it was just a transition, a moment between endings and beginnings, between death and rebirth? What if the universe breathes in and out, expanding and contracting, growing and shrinking? What if everything we see, all the galaxies, all the stars, all the matter and energy, is just one breath in an eternal rhythm, one cycle in a pattern that has no beginning and no end? This is the Big Bounce theory, and it suggests something profound. The Big Bang wasn't creation, it was recycling. The standard Big Bang model has a problem. It predicts a singularity, a point where density becomes infinite, where space and time shrink to nothing, where all of physics breaks down. At that moment, 13.8 billion years ago, the equations stop working. Mathematics gives us infinities and nonsense. We can't describe what happened because the rules themselves cease to apply. Most physicists believe this singularity isn't real. It's not a feature of the universe, but a bug in our theories. It's a sign that we're missing something, that our understanding of gravity and quantum mechanics isn't complete enough to describe what really happened at that moment. Enter loop quantum cosmology, a theory that tries to apply quantum mechanics to the fabric of space itself. In this framework, space isn't infinitely divisible. It has a smallest possible unit, a quantum of space, beyond which you cannot go smaller. Space is grainy, pixelated at the tiniest scales. When you apply this idea to the universe's history, something remarkable happens. As you trace time backward toward the Big Bang, the universe shrinks. Density increases, temperature rises, but it never reaches infinite density. It never becomes a singularity. Instead, when the universe contracts to an incredibly dense state, packed tighter than anything we can imagine, quantum effects kick in. Space itself resists being compressed further. It pushes back, and instead of collapsing into nothingness, the universe bounces. Like a ball hitting the ground and rebounding, the contracting universe reaches a minimum size and then expands again. The Big Bang becomes the big bounce, not a beginning, but a turning point, a transition from contraction to expansion. Before our universe was expanding, it was contracting. Before that, it was expanding again, and before that, contracting. An endless cycle, bounce after bounce after bounce, stretching back through time forever. Think about your breathing. Right now, your chest is rising and falling. Air flows in, air flows out. Expansion, contraction. It's rhythmic, cyclical, continuous. When did your breathing begin? When was your first breath? You had one certainly, the moment you were born. But breathing as a process, as a pattern, has no beginning. It's just a cycle that continues as long as you're alive. The universe might breathe the same way. Each bounce is like one breath. Our current expanding phase is an inhale that started 13.8 billion years ago. Eventually, maybe trillions of years from now, the expansion will slow stop and reverse. The universe will begin to contract. All the galaxies will fall back together. Space will shrink and then bounce. Another exhale, another expansion, another universe. Roger Penrose, one of the greatest mathematical physicists alive, proposed a different version of this idea called conformal cyclic cosmology. In Penrose's model, the universe doesn't contract physically. Instead, after all the stars have died, after all the black holes have evaporated through Hawking radiation, after the universe has become cold, dark, and empty, it undergoes a transformation. In that far future, only massless particles remain, photons drifting through empty space forever. And here's Penrose's brilliant insight for massless particles. Time has no meaning. Relativity tells us that at light speed, time stops. From a photon's perspective, it exists at all moments simultaneously. So, in the far future, when only massless particles remain, the universe loses its sense of time and scale. And mathematically, Penrose showed this infinite future state is equivalent to the infinite density state of the Big Bang. The end becomes the beginning. The cold, empty universe transforms into the hot, dense state that starts the next cycle. No bounce, no contraction, just a mathematical transformation. The Big Bang is the universe's senility becoming its infancy, death becoming birth without ever passing through a middle stage. Each cycle might last unimaginable lengths of time, trillions upon trillions of years, longer than we can comprehend, but it happens over and over eternally. The universe renews itself. It never truly ends, because every ending is also a beginning. Here's something fascinating. These cyclic models predict that each cycle might leave traces in the next one. Faint echoes, subtle patterns. Penrose has suggested that powerful events in the previous universe, like collisions between supermassive black holes, might leave circular patterns in the cosmic microwave background of the next cycle. Scientists have looked. They've searched the CMB for these circular patterns, these bruises from the previous universe. Some researchers claim to have found them. Others say it's just noise, just randomness, just our brains finding patterns where none exist. The evidence is inconclusive, but the possibility remains. Maybe the CMB contains messages from before our Big Bang. Maybe we can read the history of the previous universe encoded in the oldest light we can see. Maybe we're not the first cycle. Maybe we're the trillionth. Maybe there's an infinite chain of universes stretching backward, each one leaving faint fingerprints for the next. If the cyclic universe is real, then there was no first moment, no beginning, no creation from nothing, just transformation, transition, endless renewal. The universe is eternal, not unchanging, but perpetually changing, perpetually cycling through phases of expansion and contraction, or birth and rebirth. Your heart beats. Right now, as you read these words, it's contracting and expanding. Systole and diastole, squeeze and release. When did your heartbeat begin? Again, you had a first heartbeat when you were an embryo, but the pattern, the rhythm, the cycle, it has no beginning. It's just what hearts do. They beat, they cycle, they continue. The universe might be the same. It beats, not with seconds between pulses, but with trillions of years. Each bounce is one heartbeat in an eternal rhythm. We're living in the expansion phase, the moment between beats. Eventually come the contraction, the next beat, the next bounce. It's both comforting and strange. Comforting because it means the universe never truly dies. Every ending is temporary. Every death is followed by rebirth. The cosmos is immortal, in a way perpetually renewing itself, never reaching a final state. But strange because it means there's no ultimate beginning, no first cause, no moment when everything started. Existence just is, always was, always will be, cycling through different forms, but never truly beginning or ending. The cyclic universe changes how we think about the Big Bang. It's not the start of everything. It's just the most recent reset, the last time the universe refreshed itself. Before that, another universe with its own galaxies, its own stars, its own history. And before that, another, and another, an infinite chain of cosmic reincarnations. Each cycle might be slightly different. Maybe the constants change a little. Maybe gravity is stronger in one cycle and weaker in the next. Maybe the patterns of galaxy formation vary. Each universe is unique, but they're all part of the same eternal process. And here's a thought to carry with you. As you drift towards sleep, the universe needs rest between cycles. In the cyclic models, there's a moment, brief or long, depending on the theory, when the universe transitions. A pause, a breath held before the next breath begins. Just like your body needs Rest between days, between cycles of waking and sleeping. The universe might need its own kind of rest. That transition at the bounce, or that transformation in Penrose's model, maybe it's the universe's way of preparing for its next phase. So let your body prepare for its own cycle. Let your thoughts slow. Let the rhythm of your breathing become the rhythm of the cosmos, in and out expansion and contraction, waking and sleeping. The universe will be here tomorrow, still cycling, still breathing, still being, and so will you. Close your eyes now. Feel your chest rise and fall. That rhythm, that's the rhythm of everything. That's the heartbeat of existence itself. You're part of it. You're breathing with the universe. And just like the universe, you'll wake up renewed, ready for another cycle, another day, another breath. Sleep well. The cosmos is still turning, still bouncing, still being, and tomorrow we'll explore what other mysteries might lie beyond the edge of everything we know. Rest now. The universe can wait. You've just journeyed through bubble universes, extra dimensions, holographic realities, and cyclic time. But now, let's turn to something we can actually measure, something strange happening right now in our observable universe, something pulling on us that shouldn't exist. Have you ever felt drawn toward something without knowing why? Like an invisible force is tugging you in a particular direction and you can't explain it? The universe might be experiencing exactly that. In 2008, a team of astronomers analyzing data from NASA's Wilkinson Microwave Anisotropy Probe WMAP discovered something that shouldn't be possible. Galaxy clusters, the largest gravitationally bound structures in the universe, were all moving in the same direction, not randomly scattered in their motions, not distributed evenly as cosmological models predicted, but flowing, streaming, rushing toward one particular patch of sky. They called it dark flow. These clusters, massive collections of hundreds or thousands of galaxies, each galaxy containing billions of stars, were moving at speeds between 600 and 1,000 kilometers per second, not toward each other, not away from each other, but all together in concert toward the constellation Centaurus. This shouldn't happen. In the standard cosmological model, galaxy clusters should move somewhat randomly based on local gravitational influences. There should be no large-scale coordinated motion across such vast distances. It's like discovering that all the fish in every ocean on Earth are swimming in the same direction at once. Why? What's pulling them? The astronomers looked for explanations within our observable universe. Maybe there's a massive concentration of galaxies in that direction, pulling everything toward it. But the measurements didn't support that. Nothing visible could account for such powerful, coordinated motion across such enormous scales. So they proposed something radical. What if the pull is coming from outside? What if there are massive structures beyond our cosmic horizon, beyond what we can ever see, exerting gravitational influence on our observable universe? Remember, gravity doesn't respect the cosmic horizon the way light does. Light from beyond the horizon can never reach us because space expands too fast. But gravity propagates through space-time itself. If something truly enormous exists just beyond our observable bubble, perhaps a massive concentration of matter, perhaps entire superclusters of galaxies we can never see, its gravity might still affect us. It's like standing in a river. You can see the water around you, See the surface, see the waves, but beneath, invisible to you, there's a current, an underwater flow pulling everything in one direction. You don't see what's causing it, maybe a huge rock formation downstream, maybe the shape of the riverbed, but you feel its effects. The surface water moves because of something hidden below. Dark flow might be the cosmic equivalent, gravitational current caused by structures we cannot observe pulling on the visible universe from beyond the edge. But here's where it gets controversial. Not all scientists accept dark flow as real. The original measurements used something called the Sunyaev-Seldovich effect. When the ancient light from the cosmic microwave background passes through hot gas in galaxy clusters, the photons gain a tiny bit of energy. By measuring this energy shift, astronomers can determine how fast the cluster is moving. It's like measuring the Doppler shift of sound, the change in pitch when an ambulance drives past you, but for microwaves passing through hot plasma. The WMAP team analyzed hundreds of galaxy clusters and found a consistent pattern. They were all flowing in one direction. Dark flow seemed real, measurable, significant. But when the European Space Agency's Planck satellite, more sensitive, more precise, examined the same regions, the signal became less clear. Some analyses found hints of dark flow. Others found nothing beyond random noise. The scientific community split. Some argued the original detection was a statistical fluke, an artifact of data processing a pattern that wasn't really there. Others maintained the signal was real, but subtle, requiring careful analysis to extract from the noise. The debate continues. No consensus has emerged. Dark flow remains unconfirmed, neither proven nor disproven, hanging in that frustrating space where science often lives, tantalizing but uncertain. If dark flow is real, the implications are staggering. It would be direct evidence that our observable universe is influenced by things beyond what we can ever see. It would confirm that the cosmic horizon isn't a true boundary, but just a limit of observation. Reality extends beyond, and that hidden reality affects us. Some cosmologists suggest dark flow might be evidence of other universes in an eternal inflation scenario. If bubble universes exist, if our observable cosmos is just one pocket in an infinite foam, then massive structures in neighboring bubbles might pull on us gravitationally. We can't see those structures because they're beyond our horizon, but we might feel their gravity. It's like living in an apartment and feeling vibrations from the apartment next door. You can't see what's happening there. The wall blocks your view, but you know someone's home because the floor trembles, the walls shake slightly. Dark flow might be the universe's equivalent gravitational vibrations from neighbors we can never visit. Others are more skeptical. They point out that finding patterns in noisy data is easy. The human brain is built to detect patterns, sometimes too well. We see faces in clouds, hear words in static, find meaning in randomness. Maybe dark flow is our cosmic pareidolia, a pattern we want to see rather than one that's truly there. The truth we don't know yet. More observations are needed, better instruments, more sophisticated analysis techniques. Perhaps future surveys will resolve the mystery conclusively, or perhaps dark flow will join the list of cosmic anomalies that fade away upon closer inspection, like canals on Mars or the expanding Earth hypothesis. But whether dark flow is real or illusion, it teaches us something important. The universe still surprises us. Even with all our satellites, all our telescopes, all our theoretical frameworks, nature can present phenomena we don't expect, mysteries that don't fit neatly into our models, questions that remain unanswered. And sometimes the most honest scientific answer is we're not sure. We're still looking. We're still measuring. We're still trying to understand. The universe keeps its secrets well, and dark flow, real or imagined, reminds us that beyond the edge of what we can see, there might be forces, structures, realities we haven't discovered yet. Maybe never will discover, but they're out there, perhaps pulling on us, influencing us in ways we're only beginning to detect. Like an ocean current, you can't see but can't escape. But dark flow isn't the only anomaly in the ancient light of the universe. There's another mystery, literally written across the sky. In the oldest light, we can observe a cold, dark patch that shouldn't exist. You have scars, don't you? Marks on your skin that remind you of something that happened. Maybe you remember the event clearly. Maybe you've forgotten, but the scar remains. Evidence of an old wound. A permanent reminder that something occurred, even if the details have faded from memory. The universe has scars too. In 2004, astronomers studying the cosmic microwave background, that ancient light we discussed earlier, the afterglow of the Big Bang, noticed something odd. In one region of the sky, in the constellation Eridanus, there was a spot, a large area, roughly 5 to 10 degrees across, that was colder than it should be. Not just slightly colder, significantly colder, about 70 millionths of a degree colder than the surrounding regions. That might not sound like much, but in the incredibly uniform temperature map of the CMB, it's enormous. Statistically unlikely. Weird. They called it the cold spot, and it's been puzzling scientists for 2 decades. The cosmic microwave background is remarkably uniform. The temperature variations are tiny, just 1 part in 100,000. The universe at 380,000 years old was incredibly smooth, with only tiny density fluctuations that would eventually grow into galaxies. Those fluctuations show up as slight temperature differences in the CMB. Hot spots where matter was slightly denser, cold spots where it was slightly less dense. But these variations follow specific statistical patterns predicted by cosmological models. Random but predictable. Like flipping a coin, you can't predict each individual flip, but you can predict the overall distribution. The cold spot doesn't fit those predictions. It's too big, too cold, too anomalous. When the Planck satellite later examined the same region with even greater precision, it confirmed what WMAP found. Yes, it's there. Yes, it's weird. Yes, it's real. So, what caused it? The first hypothesis was straightforward. Maybe there's a supervoid in that direction. A supervoid is an enormous region of space with significantly less matter than average. Instead of the cosmic web of galaxy filaments and clusters, a supervoid is mostly empty, a vast bubble of near nothingness. When CMB photons pass through a supervoid, something interesting happens. As they enter the void, they climb out of a gravitational well, gaining energy and becoming slightly bluer. As they exit, they fall back into a gravitational well, losing energy and becoming slightly redder. Normally, these effects cancel out, but if the void is expanding as photons pass through it, which it is because the universe is expanding, the effects don't quite cancel. The photons end up slightly redder, slightly lower in energy, slightly colder. This is called the integrated Sachs-Wolf effect. In 2015, astronomers using data from the Dark Energy Survey found evidence of a supervoid in the cold spot's direction. It was huge, hundreds of millions of light years across, and it could potentially explain some of the temperature drop. But here's the problem. The math doesn't quite work. The supervoid isn't quite big enough or empty enough to fully explain how cold the cold spot is. Even accounting for the integrated Sachs-Wolf effect, the spot remains statistically anomalous. Something more might be happening. Enter the multiverse hypothesis. Remember bubble universes. Remember the idea that our cosmos might be one bubble in an infinite foam, and that bubbles might occasionally collide. Some cosmologists suggested the cold spot might be a bruise from such a collision. If another bubble universe brushed against ours billions of years ago, shortly after our Big Bang, it might have left a mark. A distortion in space-time, a region where the energy density was disrupted by the impact. That disruption would show up in the CMB as a cold spot, a circular region where the temperature is lower than expected because the collision altered the local conditions when the CMB formed. It sounds like science fiction. It sounds absurd. But mathematically, it's possible. Eternal inflation predicts bubble collisions should happen. And if they do, they should leave marks. Circular patterns in the CMB, scars from ancient cosmic accidents. Scientists have searched for these collision signatures. They've looked for circles for specific patterns that would indicate an impact from another universe. Some researchers claim to have found them. Others say the patterns are just noise, just randomness, just wishful thinking. The cold spot remains controversial. Is it evidence of another universe? Or just a statistical fluctuation combined with a supervoid? Or something else entirely we haven't thought of yet? Recently, machine learning and artificial intelligence have been brought to bear on the problem. Algorithms scan the CMB looking for anomalies, for patterns human eyes might miss, or statistical analyses might overlook. These AI systems have found other odd features in addition to the cold spot regions that don't quite fit the models, structures that seem unlikely. Maybe the CMB contains more secrets than we've realized. Maybe it's like a photograph with hidden details that only become visible when you enhance the image in just the right way. The universe has a bruise, just like you might have a mark on your shin from walking into a table corner. Last week, the cosmos has the cold spot, a reminder that something happened, even if we're not entirely sure what. And here's something that might make you smile. The universe gets bruises, just like you do. It's clumsy too. It bumps into things, or maybe things bump into it. Either way, it's marked by its collisions, scarred by its history. The cold spot sits there in the microwave sky, cold and mysterious, waiting for us to understand it. Maybe it's evidence of the multiverse. Maybe it's just a statistical quirk in an otherwise normal supervoid. Maybe it's something we haven't even considered. But it's real. It's measurable. It's strange. And it reminds us that even when we look at the oldest light in the universe, even when we study the most ancient structures, we can observe mysteries remain. The cosmos keeps secrets. It shows us scars without explaining how it got them. We're like detectives, examining evidence from an ancient crime scene. We see the marks, the traces, the anomalies. We build theories and test them. Some fit better than others. But the truth, the full truth, remains elusive. And maybe that's okay. Maybe the universe should have mysteries. Maybe some questions don't have easy answers. Maybe the cold spot will keep cosmologists awake at night for decades more, arguing, analyzing, wondering. Because that's what makes science beautiful. Not the answers we've found, but the questions that still remain. If the cold spot is a scar from the universe's infancy, then what we're about to discuss is even older. A signal from before the universe even had a face to scar. Right now, as you read these words, trillions upon trillions of particles are passing through your body, through your skin, through your bones, through every cell, every atom. They're streaming through the earth itself, through mountains and oceans, barely noticing that matter exists at all. You are part of the universe in the most literal sense. You're not just in it, it's flowing through you every single second. These particles are neutrinos, and they're the closest thing physics has to ghosts. Neutrinos barely interact with anything. A neutrino can pass through a light year of solid lead that's 6 trillion miles of dense metal and have only a 50-50 chance of hitting a single atom. They're so elusive, so ethereal, that they earned the nickname ghost particles. They see matter as mostly empty space, because from their perspective it is. We've talked about the cosmic microwave background, the light from 380,000 years after the Big Bang. That's our oldest baby picture of the universe, the earliest light that could travel freely through space. But there's something older, something that escaped even earlier, the cosmic neutrino, background neutrinos that were released just 1 second after the Big Bang. 1 second, not 380,000 years, not even 1 year. 1 second after the beginning of everything, neutrinos decoupled from the hot plasma soup and began their journey through space. They've been traveling ever since, cooled by the expansion of the universe, filling every cubic centimeter of space, with about 300 of them. These primordial neutrinos carry information from a time before light itself was free. They're messengers from the very first moments of creation, from when the universe was so hot that atomic nuclei were just beginning to form, when the fundamental forces were still settling into their current configurations. If we could detect the cosmic neutrino background, we'd be seeing the universe as it was 1 second old. We'd be probing the physics of conditions we can never recreate in laboratories, energies we can barely calculate, temperatures that strain our theoretical models. But here's the problem: detecting these ancient neutrinos is almost impossible. Remember, neutrinos barely interact with matter. The CMB we detect easily, it's everywhere, hitting our instruments, constantly, relatively easy to measure. But neutrinos, they pass right through our detectors, like ghosts through walls. Most neutrino detectors catch maybe a handful of high-energy neutrinos per day from sources like the sun or supernovae. The cosmic neutrino background is even more challenging. These neutrinos have been cooled by cosmic expansion for 13.8 billion years. They're low energy, moving slowly, compared to the speed of light, incredibly difficult to catch. Building a detector sensitive enough to capture them is one of the great technical challenges in physics, but scientists are trying. There's an experiment called Ptolemy, the Princeton Tritium Observatory for Light Early Universe Massive Neutrino Yield, designed specifically to detect relic neutrinos from the Big Bang. It uses tritium, a radioactive form of hydrogen, and looks for the tiniest energy shifts. When a primordial neutrino happens to interact with a tritium nucleus during its decay, it's like trying to hear a whisper in a hurricane. The signal is so faint, the background noise so overwhelming, that detecting even a single event with certainty requires extraordinary precision and patience. But if Ptolemy or a future experiment succeeds, it will be revolutionary. We'll have confirmed one of the last major predictions of Big Bang cosmology. We'll have direct evidence from the first second of the universe's existence. We'll have opened a window into physics at energy scales we can barely imagine. Why are neutrinos so important for understanding the early universe? Because they witnessed everything. They were there when quarks combined to form protons and neutrons. They were there during Big Bang nucleosynthesis, when the first atomic nuclei formed. They were there before atoms existed, before light could travel freely, before anything we can currently observe was observable. Neutrinos are time capsules, perfectly preserved messages from the beginning, waiting for us to develop the technology to read them. Think about wind. You can't see it, can't touch it, can't catch it in your hands, but you know it's there. You feel it on your face. See trees swaying, watch leaves scatter across the ground. Wind is invisible, but everywhere present, but intangible. Neutrinos are the universe's wind, invisible, intangible, but everywhere, constantly flowing through everything, rarely stopping, rarely interacting, just passing through on their eternal journey from the moment they were born. And you are swimming in that wind. Every second, roughly 100 billion neutrinos from the sun alone pass through every square centimeter of your body. You never notice. They leave no trace, but they're there connecting you to the nuclear fusion happening in the sun's core, to the cosmic processes that power stars, to the fundamental physics that makes existence possible. The cosmic neutrino background adds trillions more, ancient neutrinos from the first second of time, carrying information from an epoch we cannot otherwise access. You are constantly bathed in messages from the beginning of everything. We're approaching the boundary of knowledge now, the edge, not of space, but of understanding. We've journeyed from galaxies disappearing beyond the horizon, to bubble universes, to extra dimensions. We've discussed holograms and mirror universes and cosmic bruises. But with the cosmic neutrino background, we're reaching a place where questions outnumber answers, where theory outpaces experiment, where we know what should exist but can't yet prove it does. This is the frontier. Not a physical place, but a conceptual one. The limit of what we can currently test, currently verify, currently know for certain. And it's exhilarating, because frontiers are where discoveries happen, where new knowledge emerges, where mysteries transform into understanding, slowly, painstakingly, one careful experiment at a time. The neutrino ghosts are out there flooding through the cosmos, carrying secrets from the first second. We just need to learn how to catch them, how to listen to their whispers, how to decode the messages they've been carrying for nearly 14 billion years. And when we do, we'll hear the universe speaking to us from its infancy, telling us stories we've never heard before. But neutrinos aren't the only messengers from beyond. There's another signal, even more fundamental, that might carry information from places and times no light can reach. Imagine you're in an apartment and loud music starts playing next door. You can't hear it. Through the walls, the soundproofing is too good, but you can feel it. The bass vibrates through the floor, through your furniture, through your body. You perceive the music not as sound, but as rhythm, as vibration, as something transmitted through the structure itself. Gravitational waves are like that. They're vibrations in the fabric of space-time itself. And unlike light, they pass through matter almost unimpeded. On September 14th, 2015, humanity heard the universe for the first time. Two detectors in the United States, LIGO, the Laser Interferometer Gravitational Wave Observatory, picked up a signal, a tiny vibration in space-time, stretching and squeezing the fabric of reality by less than the width of a proton. The signal lasted a fraction of a second, rising in frequency and amplitude before cutting off abruptly. Physicists immediately recognized what it was: two black holes each, about 30 times the mass of the Sun, spiraling into each other more than 1 billion light-years away. As they circled faster and faster, they emitted gravitational waves, ripple in space-time itself. Finally, they merged, creating a single larger black hole and releasing more energy and gravitational waves than all the stars in the observable universe emit in light at that moment. Einstein predicted gravitational waves exactly 100 years earlier, in 1916, as a consequence of general relativity. If massive objects accelerate, they should create ripples in space-time that propagate outward at light speed, carrying information about the events that produced them. But Einstein himself doubted they'd ever be detected. The effects are so small, the distortions so tiny, that it seemed impossible to build instruments sensitive enough to measure them. A century later, we proved him wrong. We can hear the universe now, not with light, not with particles, but with gravity itself. Gravitational waves have a unique property. They're incredibly hard to stop. Light gets absorbed by dust, scattered by gas, blocked by plasma. Neutrinos barely interact, but can still be deflected by intense magnetic fields or extreme densities. But gravitational waves, they pass through everything. Matter is essentially transparent to them. This means gravitational waves can carry information from places and times that light cannot reveal. They can tell us about the interiors of colliding neutron stars, where matter is crushed to nuclear densities. They can show us what happens at the event horizon of black holes, where space-time curves so severely that light cannot escape, but gravitational waves can. And most intriguingly, they might carry signals from before the cosmic microwave background. From before, light could travel freely, from the first moments after the Big Bang itself. If violent enough events occurred during cosmic inflation, or immediately after, they would have produced gravitational waves. Those primordial gravitational waves would have traveled unimpeded through the opaque plasma that trapped light. They'd be out there now, stretched to incredibly long wavelengths by cosmic expansion. carrying information from a time we cannot otherwise observe. Detecting these primordial waves is extraordinarily difficult. Current detectors like LIGO are sensitive to high-frequency gravitational waves from black hole and neutron star mergers. Primordial waves from the Big Bang would be much lower frequency wavelengths, the size of the observable universe itself. Future detectors might catch them. The planned laser interferometer, space antenna, LISA, will launch in the 2030s, floating in space, sensitive to lower frequency waves than Earth-based detectors can measure. It might detect signals from the early universe, from supermassive black holes, colliding from cosmic strings, if they exist, and beyond LISA, perhaps detectors that use the cosmic microwave background itself as an instrument looking for subtle patterns imprinted by gravitational waves. Perhaps arrays of pulsars rapidly spinning neutron stars that act as a galaxy-sized detector. The technology continues to evolve. Gravitational waves are often called the sound of the universe. Not sound in the traditional sense, sound needs a medium, like air or water, to propagate through, and space is vacuum. But gravitational waves can be converted into audible frequencies, and when physicists do this, you can literally hear cosmic events. The black hole merger LIGO detected sounds like a chirp, a rising tone that ends with a sharp thump. Each merger has its own signature, its own pitch and rhythm. The universe is playing a symphony, and we've finally learned to listen. Some cosmologists speculate that gravitational waves might carry echoes from other universes. If bubble universes collide, if brains crash together, if the multiverse is real and interactive, then these events might produce gravitational waves that propagate through multiple realities. We might detect a signal one day that doesn't match any event in our observable universe. A wave that seems to come from nowhere, caused by nothing we can see. And we'll have to ask, is this an echo from beyond, a message from a neighboring bubble, evidence of realities beyond our own? It's speculative, far from proven but not impossible. Gravitational waves might be the universe's way of communicating across boundaries that light cannot cross. Think about standing on a wooden floor while someone plays music in another room. You don't hear the melody clearly, but you feel the vibrations through your feet, through the structure of the building. The music reaches you not as sound, but as physical rhythm transmitted through solid matter. Gravitational waves work similarly. Their vibrations in the structure of space-time itself, ripples that spread outward forever, carrying information about the events that created them. When they pass through Earth, they compress and stretch space by infinitesimal amounts. We can't see them or hear them in the normal sense, but our instruments can feel them, can detect the subtle rhythm of distant cosmic catastrophes. When you drop a stone into still water, ripples spread outward in perfect circles, moving forever until they encounter a shore or fade into imperceptibility. Gravitational waves are like those ripples, but in the fabric of reality itself. They spread outward from every violent cosmic event, traveling at light speed, carrying information forever. The merger that LIGO detected happened over 1 billion years ago. The gravitational waves from that event traveled through expanding space for all that time, finally arriving at Earth on September 14th, 2015, we caught an echo from the distant past, a vibration that had been traveling since before multicellular life evolved on our planet, and it's still traveling. The waves continue beyond us, spreading through the cosmos, carrying their message to whatever civilizations might detect them 1 billion years from now, 10 billion years forever. Every violent event in cosmic history creates waves that never fully disappear. The universe is filled with overlapping gravitational waves from every black hole merger, every supernova, every cosmic collision since the beginning, a symphony of space-time vibrations, most too faint for us to detect individually, but they're all still propagating. We're learning to listen, to hear the universe not with light, but with gravity. And what we're hearing is teaching us things we could never learn any other way about the most extreme physics, the most violent events, the deepest mysteries of how space-time itself behaves. The universe is speaking, and finally, after billions of years, we're learning its language. And now, as we near the end of this journey, let me bring together everything we've explored and leave you with one final thought as you drift towards sleep. We've traveled far together, from the edge of the observable universe to bubble multiverses, from extra dimensions to holographic projections, from mirror universes running backward through time to cosmic bruises in ancient light, from ghost particles to gravitational waves. We've asked what exists outside the edge of the universe, and we've discovered that the answer isn't simple. It might be infinite space, stretching forever, with more galaxies, more stars, more versions of you, living slightly different lives. It might be other bubble universes with different laws of physics, where reality operates by rules we cannot imagine. It might be extra dimensions. We cannot perceive hidden directions perpendicular to everything we know. It might be that we're a hologram, a projection from a lower dimensional boundary. It might be that there's a mirror universe on the other side of time running backward. It might be that the universe cycles endlessly, bouncing from expansion to contraction to expansion, again eternal and self-renewing. Or it might be that the question itself is meaningless. Maybe there is no outside. Maybe the universe is all there is, self-contained, requiring no external space to expand into, because space itself is what's expanding. We've encountered mysteries, dark flow pulling galaxies towards something beyond the horizon, the cold spot marking our ancient sky with unexplained coldness, neutrinos carrying messages from the first second of time, gravitational waves rippling through space-time from events we cannot see with light. Some of these mysteries might be solved. Others might remain forever beyond our reach, hidden by fundamental limitations of physics, the speed of light, the cosmic horizon, the quantum nature of reality itself. But here's what I want you to understand. Maybe you'll never know the complete answer. Maybe humanity will never know. Maybe the full truth about what lies beyond the edge is fundamentally unknowable, separated from us not by technology or intelligence, but by the basic structure of causality. And that's okay, because asking the question, wondering, exploring, imagining, that's what makes life meaningful. That's what makes us human. We're curious creatures. We look at the horizon and wonder what's beyond it. We see the stars and want to reach them. We encounter a mystery and cannot rest until we've tried to solve it. This drive, this need to know, to understand, to explore, it's core to who we are. You might never visit another galaxy. You might never detect a gravitational wave. You might never see evidence of another universe. But by asking these questions, by learning about the edge of knowledge, you've participated in humanity's greatest adventure, the quest to understand reality. And here's the good news: the universe still has mysteries, plenty of them, which means you'll never run out of things to wonder about before you fall asleep. Your mind can wander through infinite possibilities, exploring ideas too vast for any laboratory, too strange for any experiment. Exploring the universe is like reading a great book. You want to know how it ends. You want to reach the final page and have all your questions answered. But you also don't want it to end, because the journey itself, the act of discovery, the unfolding of understanding, is so satisfying that you wish it could last forever. We're in the middle chapters of humanity's cosmic story. We've learned so much. The universe is vast beyond imagining. Time and space are stranger than we thought. Reality might be woven from information, from quantum fields, from dimensions we cannot see. We're surrounded by mysteries, dark matter, dark energy, the quantum nature of gravity, the possibility of other universes. And that's beautiful, not frustrating, not disappointing. Beautiful, because mystery is what drives us forward. It's what makes tomorrow worth exploring. It's why we build telescopes and particle accelerators and gravitational wave detectors. It's why we ask questions and test hypotheses and peer ever deeper into the nature of things. Could we be at the edge of another universe's observable region? Could beings in a bubble next to ours be wondering the same questions, looking at their cosmic horizon, asking what lies beyond? Are we the mystery for someone else? Maybe, probably, almost certainly, if the multiverse theories are correct. Somewhere in some bubble or dimension or parallel reality, there might be others wondering about us. We might be their edge, their boundary, their unanswerable question. And just as we cannot signal, them cannot send light or messages across the inflating space or through higher dimensions, they cannot signal us. We're separated not by hostility or ignorance, but by physics itself, the ultimate loneliness and the ultimate companionship, surrounded by countless others, all asking the same questions, all forever alone. But there's hope in this story. We've come so far. We've learned so much. A century ago, we thought our galaxy was the entire universe. Now we know it's one of trillions. We thought the universe was static. Now we know it's expanding, accelerating, dynamic. We thought the Big Bang was the beginning. Now we consider bounces and cycles and eternal inflation. Who knows what we'll discover next? What mysteries will be solved? What new questions will emerge? The journey is what matters, not the destination. Because in cosmology, there might be no final destination, just an endless horizon, forever receding, forever beckoning us forward. So, let these thoughts about the universe drift with you into sleep. Don't worry about the edge of the universe. It will take care of itself. It's been expanding for 13.8 billion years without your help. It can manage another night. While scientists stay awake pondering these mysteries, running calculations, analyzing data, you can rest. You've wondered. You've explored. You've touched the edge of human knowledge. Now, Let your mind relax. Who knows? Maybe in your dreams you'll find answers. Maybe your unconscious mind will make connections that elude us while awake. Maybe you'll journey through the multiverse, visit bubble universes, slide through extra dimensions, witness the big bounce firsthand. Or maybe you'll just sleep deeply and peacefully, your brain processing everything you've learned, consolidating memories, resting before tomorrow's adventures. Either way, you've earned it. The universe is vast, beautiful, strange, mysterious, and it will still be here tomorrow, still expanding, still full of wonders, still inviting you to look up and wonder. So close your eyes now. Feel yourself breathing in and out like the universe expanding and contracting, like the eternal rhythm of existence itself. You're part of this cosmos. You're made of stardust. Your atoms were forged in dying stars billions of years ago. You are the universe experiencing itself, asking questions about itself, wondering about its own nature. And that's extraordinary. Sleep well. Dream of galaxies. Dream of dimensions. Dream of universes beyond universes. Mysteries beyond mysteries. Wonders beyond imagination. And when you wake, the cosmos will still be there, waiting for you to explore it. Good night, and may your dreams carry you safely through the multiverse and back again.